Hello and welcome back to Calculus 1, section 2.3 on techniques for computing limits. So far in 2.2 we explored the basic two ideas to compute limits, graphic approach and charts and tables, which with values, right? So you compute numbers. So those will be the first two techniques that you maybe can keep as a last resort, I guess. We want to compute limits, if possible, using algebra and plug-in method. So, number one, we already covered in 2.2, graph. Number two, also in 2.2, chart or table or values. Number three, plug-in. That one is, we have to discuss that. Number four, algebra. So these are the ways. 3 and 4 are obviously in this lecture. So we said about the that the limits compute the y value of the function, and we have seen that for that example of x cubed plus 1, f of 2 was 9, and the limit of x cubed plus 1 as x goes to 2 was 9. This tells us that you are allowed to plug in a value and actually get the answer. And that is the fastest way. But it's not going to work all the time. So, number 3, plug in. Here, I'll write this in blood. We cannot use this if the denominator is 0. So these are some of the very important points. So if you have, let's say, a limit of 1 over x squared as x goes to 0, and you go, oh, that's 1 over 0, and then you write does not exist, and I'm not happy. Because the limit is actually positive infinity. And you plugging in a value clearly doesn't work. You cannot divide by 0. So, no. I have to cross it out. I have to cross it out. And you better cross it out in your notes too. When can I plug in? I can plug in to check anytime, but then if I get an answer, like 7 or 1/2 or whatever, yeah, we're good to go. But if you get 0 in denominator, you immediately have to discontinue the plug-in method, because it can give you the wrong answer. And also, in certain situations, the infinities arise and all of these kind of things. So calculus is really open, right? In pre-calc, we are very careful to give you examples that fit the basic ideas of pre-calculus. Calculus can chew through anything, right? And because it's so powerful, anything goes. That just means that you have to be more careful. So if I do get the question like this, which we'll actually cover in a greater detail later, I want to graph this one because it looks like that, and I see it's positive infinity because both of these go up, right? So when can I use plug-in method? Plug-in method works when I have the limit as x goes to 3, and then I have a square root of x squared minus 5, right? So in this case, you clearly are getting the nice value, and there are no denominators and negatives under the square root, negatives in the ln, none of the weird stuff. And because none of the weird stuff happened, you were able to compute the value. And everyone's happy. So very limited amount of problems in calculus and beyond will actually have this method possible, because why would you use a sledgehammer if the small hammer, which is pre-calc, is going to solve the problem, right? Technically, you are hacking this problem and doing it the pre-calc way, plug in a value. Remember what we said about the limit. Limit computes everywhere except at the value. So you're kind of cheating with the plug-in method. But the plug-in method works for the basic stuff. So what we say, don't use a sledgehammer to put the painting on a wall. Use the regular hammer.
So you're never going to use like variable restrictions when you're dealing with limits. Because I know like when obviously in like algebra when you divide like by a variable that you don't know could possibly be 0, you're like a cannot equal 0. You know what I mean?
Yes.
So you're never going to utilize that technique when you're dealing with
Well, remember, x goes to 3, so you know exactly what's happening. Okay. You see, we are going to deal with the limit like this. Limit sine x over x as x goes to 0. Mm-hmm. You're looking at this, mm-hmm. and you say, well, if I plug this in, I get sine of 0, which is 0, and then I plug 0 on the bottom is 0 divided by 0. Mm-hmm. Now, anything divided by 0 divided by any number is 0, right? Mm-hmm. And then you can't divide by 0. But the answer for this question is 1. Welcome to calculus. So there will be a lot of stuff that you will have to deal with in a calculus. And the good thing about the limits is that you know your input. Okay. So you don't have to have that thing in the head, keeping that thing in the head that, oh, but x could be 0, it could be 7, or it could be 3/2. Because you know exactly in the limit what it is. It goes to 0, or goes to 2, or goes to 3/7. So it's spelled out. But you run into issues as the problems I showed before, and this problem here. So guys, plug-in method is a hack, right, method. It works in a limited amount of examples. And yes, it is the first thing that you should always try. Because if you can beat the system, by all means, please beat the system. That's called efficiency in life, okay? Now, in most cases, you guys are going to end up with 0 in denominator or some other crazy thing going on. And if you have that situation, hello, algebra. How do we deal with this? And then we are going to make it even worse. But this kind of stuff is for chapter 4. So we have to wait, okay? So, you know how there are levels to hell? Let's stay within the first 2 levels now, and then we'll crank the heat as we go on. So let's take a look at some examples. Another example where you can plug in would be, let's say you have a linear line, 3x minus 2, as x goes to 8. Well, we are allowed to do this because it works. The answer is 22. So clearly it works in this situation. If you have a rational function, 1 over x minus 5, as x goes to 5, this is where we cannot plug in because 0 in denominator. You have to discontinue the method right away. So let's take a look at algebra. What happens if you have 0 in denominator? Well, it's not all lost, right? You can do the graphs and charts. So if you do have the limit x goes to 5 and you want to deal with x minus 5, it is your job to know that the minus 5 part means shift 5 where?
Shift 5 to the right.
Beautiful. So when you add and subtract numbers to x, shift is left, right. If you add and subtract number to the entire function, it's up and down. That's in your pre-calculus course for the basics of shifting functions around. So I'm going to graph this and look at it and see what the graph is. So how do I deal with this problem? The first thing is I'm going to graph it, and since I don't have calculator, I have to know how to graph this by hand. So how do I graph 1 over x minus 5? I know that graph for 1 over x looks like this. It has the horizontal and vertical axis to be the asymptotes. And now the orange tells me that I should shift 5 units to the right. That means that the vertical asymptote that was at 0 is now going to be at 5. So this is my y-axis. 1, 2, 3, 4, 5. And here is my vertical asymptote at 5. And I draw the function in there. Now, Juliet is going to walk towards 5. She's going to walk down the line, and she's going to fall off the graph to negative infinity. So, limit of 1 over x minus 5 as x goes to 5 minus, which is from the left, is giving us negative infinity as the answer. Romeo is going to approach from the right, he's going to walk up the line, and he is going to go up towards the positive infinity, making the blue limit x goes to 5 plus of 1 over x minus 5 to give us positive infinity. All together telling us that the overall limit x goes to 5 of 1 over x minus 5 is what? What's the limit? What does the theorem say? If they're the same, that's the limit. If they're not the same, does not exist. So please use all of your mental power now and tell me, are the red and blue the same?
There's no limit. It doesn't matter.
Thank you very much. Boom. Does not exist. This is how you use the theorem to solve any problem. Any. I couldn't plug in, so I used my knowledge in algebra to graph basic functions. Shift 5 units to the right as you command, right? To and then use the Romeo and Juliet, and if they have the same numbers or different numbers, right? You have to do this sometimes. Let's take a look at other examples. Limit of x squared minus 25 over x minus 5 as x goes to 5. Do we plug in? No. Why not? Because 0 in denominator. Very good. So what should I do? We could graph. Can we do anything else? Simplify. Use the algebra. And algebra is, we factor the numerator, right? Cancel and see if the equivalent problem is easier to solve. You have to write this limit over and over and over again until you use it. So the numerator factors x plus 5, x minus 5, divided by x minus 5. These die off. And you are left with the limit x goes to 5 for x plus 5. Can we plug in now? Yeah. And what's the answer? 10. So what's the limit of x squared minus 25 or x minus 5 as x goes to 5? 10. So one of the ways to use the algebra, let's go here. We see shift graphs, right? So you can, and now factoring. Let's see if we can find more. Something fun. How about limit of x minus 9 square root of x minus 3 as x goes to 9, to make it worse. Can you plug in? No. Square root of 9 is 3, 3 minus 3 is 0, 0 in denominator, can't plug in. Maybe it would be good for you to write that in notes if you ever look into notes. Right? You can maybe write a paragraph. Try to plug in, and then it didn't work. Right? What now?
I thought like you added the square root, but like you know when you add a square root, the square root of plus or minus square root. You just add it. That's the equation, so it's not this.
Yeah. So what should we? Yes. Okay, how would you do that?
I can't do mental math right now.
Alright. So you want to multiply by 1 in a way to kill the square root in the denominator.
Basically.
That's called rationalizing in mathematics.
Yes.
And yeah, you can multiply top and bottom by root x plus 3, and See how far that gets you. Because that's 1. Let's see how your algebra holds up from this point on. I'm just going to give you a quick tip and suggestion. Don't foil the top, only the bottom.
Cause I'm nice. One side of it. Other than that, you would don't know. No, you just came like this. You know what the software did? Just to figure out where the driver is that will turn it off. I have real orders. At one point, on the president select one of the players to mark None. Because he set them up for mine on Friday, hoping to do one for the weekend. But probably they just do the main switch. Shut them all down. So they were mining only for maybe 5-6 hours before they were shut down. Good. Okay.
You all have 7? 7? No? Good, because that's wrong. Yeah, 6 is good. 7 is wrong. Good. Let's talk. Limit x goes to 9. Going to leave this foil on the bottom. The midterms are going to cancel. So I have x minus 9. These guys cancel. I have limit of root x plus 3 as x goes to 9. And this is root 9 plus 3, which is 6. Nice. Let's take a look at the boss way to do this problem. Same problem. What I'm going to do is I'm going to factor the numerator. Yeah, I know, I'm looking at your faces and you're going, what? And I say, yeah, this is algebra on steroids now. What do we know? We know that a squared minus b squared is a minus b, a plus b. We better know this, we're sitting in calculus. Now, if I have, let's say, x minus 2, can I factor this? The answer is yes, because I can write square root of x squared minus square root of 2 squared, which would give me square root of x minus square root of 2, square root of x plus square root of 2. You can factor anything at any point in time. Bueno? So by this token, the top will factor into root x minus 3, root x plus 3, divided by root x minus 3, which is what you have. Those die, and there's your 6. Which is why it's called the boss way. Right?
But that'll only factor if the
It's a negative.
number is, well, I guess it's not, you're right.
No, anything goes.
Yeah.
Anything goes. But you are going to get a root or you're not going to get a root, right? Depends whether you have a 9 or a 7, right? If that was x minus 7, it would be root x minus root 7. Mm-hmm. Because it's a 9, it's root x minus 3.
Okay.
Because root of 9 is 3. So, yeah, there is that. Yay. Properties of limits. So, there are properties of limits that we are going to use to break down more complicated limits into the simpler limits so that we can compute them in smaller chunks. Right? It's like if you have a cake, you don't eat the whole cake, you break it into slices, right? And eat it. Otherwise, you'd be me. Yes. One sitting. Sum. Limit of f plus g as x goes to a is a limit of f plus limit of g as x goes to a. So if you have a function, well, it's sum of two functions, you can do individual limits and then add everything at the end. Difference. Limit f minus g, x goes to a, is limit f minus limit g as x goes to a. Three. Scalar multiple. This is a limit of c times some function of f of x, right? These are all f of x, g of x. Just lazy to write all of that. So the c is a constant. You can kick it out in front of the limit and just focus on solving the limit of a function. And then whatever you get from that calculation, multiply by c. So constants can be kicked outside. Number 4, product. Limit of f times g is limit of f times limit of g. This works only for limits. It will not work for derivatives and it will not work for integrals. It only works for limits. This is all x goes to a. And finally, not finally, sorry, 3 more. Quotient. Limit x goes to a of f divided by g is limit of f divided by limit of g. G cannot be 0. That needs to make sense, right? Because you can't divide. I'm going to combine 6 and 7 in the same rule because it deals with the exponent. When I write the exponent, they have integer exponents and then fractional exponents. it's the same thing. So any kind of exponent you have. So I'll just say exponent. So limit f to some exponent n, whether it's a whole number or fraction, as x goes to a, is going to be the limit of f of x, and then you apply that exponent on the when you are done with the limit. So they can swap, right? You don't have to do exponent first. You can do the limit first and then do the exponent later. So these are the properties of limits. You can solve cute problems with this, and you'll have a whole bunch of these in homework. When it says, you know, limit x goes to 2 of f of x is 8. Limit x goes to 2 for g of x is negative 5. Limit x goes to 2 for h of x is equal to 1. Find the limit of h is 1, bad, that's bad. Let's go with 2. So find the limit of f g divided by h squared as x goes to 2. Well, you just use the rules. You know that the limit of f times the limit of g divided by the limit of h, everything squared. Instead of limit of f, you will put 8. Instead of limit of g, you'll put negative 5. Limit of h, you'll put 2 and square it, and the whole thing is negative 10. Does this problem make sense? We use the rules to break the problem that was all grouped together with all functions on a pile. We use the rules to break it apart. Product breaks into product, quotient into quotient, and square comes out. Good effort. So when you look at this, you are replacing the entire block with 8. So this thing is here, and it gets replaced with that. And limit for g, which is this, is negative 5. So you take the whole block out and you put the new block in. So what they say, mechanics. They're not mechanics, they're Lego experts. They don't fix stuff, they replace the whole part. I know actually mechanic in America. He fixes parts, and then the car works. Not just buys a new part. That's a mechanic. When you go to the dealership, it's a Lego expert. Do we have anything else here? The squeeze theorem, and we're done. And I guess we're done for the day. What happened?
Can you combine limits that have different approaching sections? So if I have a limit, f of x, limit approaching, say 1, can I combine that with something that says f of x approaching 2?
No.
Okay.
Because they are approaching at different values. Remember, you are computing, the limit is the y value at the certain x. So that's why you can't combine them. They are in a different time zone. The squeeze theorem. known as the sandwich theorem. So if you are reading other books and run into the YouTube material, sandwich theorem doesn't mean it's time for lunch. It means it's time for more limits. So what is this squeeze theorem or a sandwich theorem? Sandwich theorem is a really, really good title for it, because you are considering function f of x that has a very erratic behavior. So something that goes right like that, and then they're asking you, what's the limit at 0? And you look at a graph and you say, I have no clue. This function is insane. What squeeze theorem does is, squeeze theorem is asking you to find a function on the top and a function on the bottom that are going to sandwich your erratically behaving function. And if all of these limits here match up, well, guess what? That's the answer, right? So, what do we have? Let's talk about the sandwich. Bread, cheese, if you're allergic, 2 slices, please. And then more bread. Look, if I'm holding the bread piece, wherever I go with the sandwich, whatever is sandwich inside has to go as well. So, if everything goes to 2 and it's here, it's there. So, your job is to find 2 functions that are going to squeeze or sandwich in the bad one. And if the red and blue limits give you, let's say 7, then the one that is sandwiched in between has to be 7. Because they all have to go together at all times. So let's take a look at the example. And this is one of those times where I generally use what they have in a book, because these examples are very rare. Limit x goes to 0 of x squared sine 1 over x. Want to try solve this one? See, 1 over x, when you plug in 0, that tries to be infinity. And then you're trying to squeeze infinity into sine and multiply that by 0. Right? Take some time, appreciate it.
There's probably a better way.
Exactly. There is actually a really cool way, but see, you know, if you want to plug in, it doesn't work. So what's the better way? Well, we have to go back and consult our knowledge of trig. Sines and cosines are bounded by 1. Sine x and cosine x are bounded by 1. This will pop up in Calc 2 and the rest of your life. So remember it. Now that means that absolute value of sine 1 over x is bounded by 1. Technically, what I said with this statement is that the range of sine and cosine is from -1 to 1. And you better know that because these waves, sines and cosine, never go away from -1 to 1. Right? That's it. -1, +1. So when I say bounded between -1 and 1, that means that your sine 1 over x is in between -1 and 1. Now you compare this to this and you realize that you are missing something. What are you missing? What am I missing? What do you mean? What am I missing when I compare these two things? X squared, thank you. So, times x squared times x squared times x squared. What do I get? I get x squared less than x squared sine 1 over x less than x squared. This negative x squared on the left side. What I just did is I squeezed the badly behaving functions between two jokes. Right? So now the limit of -x squared as x goes to 0 is 0. And the limit of x squared as x goes to 0 is 0. So what happens with the one that is squeezed in between? Has to be 0. By squeeze theorem. Because it's squeezed in between. Right? The cheese has to go anywhere I take the bread. Right? Because it's squeezed, sandwiched in. So your function over here is sandwiched between these two functions. These two functions ended up at 0, so this one has to end up at 0 because it's squeezed in there. If I take this and put it here, all of it is there. And I'm not touching the cheese, as you can see. I'm only holding the bread and put it different places. So that would be the squeeze theorem. Your job is to construct these functions. And you've seen the way you construct them. You always have this, so you construct from there, the way I did it. Bounded, and then multiply what's missing and so on. Yes?
So where did the x squared come from?
From the requirement that I have to make this function here look the same as this function here. Let me change the colors of this so it pops up more. So when I did this, the black writing on the bottom had no x squared, right? But I have to make this look the same as this, which is why I multiplied all three sides by x squared. So I didn't make it up. I just followed the steps of creating the function. Yes?
So is there any other place where you advise this method aside from trigonometric limits?
No, because trigs are the ones that are very, very difficult because it is periodic function and they don't behave well at all. If you want to think about the limit of sine x goes to infinity, well, the limit does not exist. You can just say that the limit is bounded, but does not exist because it oscillates. And that's going to be your alternating currents and all of these things you must know, right? So yeah, we are keeping this mainly in the trig department. It's not impossible to have other things, but yeah, mainly this, and 100% of the time you are responsible to build the function, right? You are not just making stuff up and stacking the deck. Oh, this is easy, let me do this instead, right? No, you have to build. So yeah, that's that. That's 2.3 algebraic way. So guys, the first method is to plug in. If you see 0 in denominator, give up immediately and start factoring, rationalizing, squeeze theorem, whatever other witchcraft you can come up with to get to the. If all fails, graphs and charts. We don't want to do charts because it's just too much. Imagine, see, when the expressions get crazy and long and a lot of computation stuff happens, are you going to compute 6 values or 7 values? The other thing is also, when you have the function that oscillates, exactly the example that you said, right, how do you know? Because it's going to ride up and down and up and down and up and down. How do you know that it's actually showing you the pattern, right? Maybe you have to compute 10,000 points, which for you guys is easy because you write it through the code. Do that for you, right? Put a little loop there and you pop it in a chart, right? In an array. But, you know, certain things over here are solved that way. Yeah. But then you don't get to practice your math skills, right? Why? That's true as well. All right, let's close this off. Bye.